In this video, we take a look at some very important theorems to help us identify how to take care of limits analytically, right? Using some algebra, some other techniques to help us work through limits when we don't have a table or graph, right? That will kind of always be our fallback, and we can use that information paired with what we're going to learn in this video to really help us cement in the details of these limits and how things go. Okay, so first I want to start kind of where we left off from looking at limits analytically. In the last video, we talked about a lot of these properties, kind of the basic ways that we evaluate limits analytically. Most of that was focused on direct substitution and then some of the other properties. So I'm gonna use those here. But again, from where we left off, we started with this example. The limit as x approaches 2 of x squared minus 4 divided by x minus 2. Okay, and what we did was we looked at a table and a graph and we were able to determine the value of this limit. Some of you might have looked at this and said, well, x squared minus 4, I can maybe factor that, right? That's a difference of squares and I can adjust that. And the first thing we notice, of course, is that I can't really direct substitute here because f of x, this guy, I can't just plug in 2. 2 is undefined, all right? So I'm not going to be able to evaluate this right away with direct substitution, okay? We know the value of this limit from before, from section 2.2, and we know that it's 4, okay? But we can't show it, like I said, with direct substitution. So I want to try to find another way to do that. And the approach that we'll take is the following. We're going to try and find a different function, another function that will help us. Excuse me. In this case, I'm going to rewrite things here. Here's my function. I'm going to factor. Right? And when I factor that, again, that difference of squares breaks down rather nicely. Factors to x minus 2 times x plus 2. Okay, and we see that I can cancel x minus 2's there. I have to be careful when I do that. Watch what happens. I say that this is about equal to x plus 2. And that about equal is kind of important. Okay? I can't say that these two things are exactly equal because for what's in yellow there, I can't plug in 2. And what's in purple, I can plug in 2. So they are not the same. But the limit as x approaches 2 of x plus 2 is 4. And that's what we know our limit to be from our graphical and numerical approach. Those two values are the same. That's going to be true just about all the time, as long as this purple function is going to satisfy some specific things. Why? Why does this happen? Well, what we have is a theorem to help us describe that. Theorem 2.7 goes just like this. I'm going to write, the words of the theorem and get that kind of out of the way and kind of explain as I go kind of what's going on, the background. But the gist is that I'm trying to find a different function that behaves the same way. Let c be a real number, and also let f of x and g of x be the same function for x not equal to c in an open interval containing c. Okay, so we say that in a specific way. But the important bits here is that f and g are exactly the same for all x that aren't equal to c. Okay, now c is where I'm going to send x, right? That's where I'm letting x approach in my limit. They're the same everywhere except at that point. Okay? If the limit as x goes to c of g of x exists, then I can say, in fact, that the limit as x goes to c of f of x also exists. And the punchline is that those two limits are the same. Because these functions behave the exact same way everywhere except right at c, but just around c, to the left and to the right, these functions behave the same. So I can say that they share the same limit. This is exactly what we'll use when we try to find another function that behaves like the original function in our limit to evaluate that limit. Okay, let's look at an example. I'm going to try to use back to this example real quick. I want to say a few more things. trying to use the same colors to match up f and g. So what we really do here is we factor and cancel. We say that these two functions are equal, and I've written my equal sign in red there because it's something that you need to pay attention to, as long as x is not equal to 2. Okay, I can say those are equal as long as I have that extra bit that x is not 2. Okay, so that means that I can use x plus 2 as my function for finding the limit of f of x. Theorem 2.7 tells us that the limit as x goes to 2 of my original function, f of x, is the same as the limit of my new function as x approaches 2. And that is just 4. Right? The method we're using here is just something that I like to call factoring and canceling. All right, there's kind of a whole bunch of limits that fall under this little subcategory. We're solving this limit analytically. We're using Theorem 2.7 to do it, and one of the types is with factoring and canceling. So, a different limit to look at, as x approaches minus 3 of the quantity, the function, x squared plus x minus 6 divided by x plus 3. Okay? So I imagine something similar happens. I can kind of go right to factoring and canceling, but I don't want to waste too much work if I don't have to. Okay? I imagine that there's something that's going to happen here, but I want to show you kind of an indicator of how we can tell. Okay, so what I try to do is I try to direct substitute right away. I try to plug in -3 to the numerator and denominator, and I see what happens. I write it like this. I use arrows, and that's because I'm saying that the numerator is approaching. 9 is -3 squared, plus a -3 minus 6. Denominator is approaching -3 plus 3. So as a whole here, the numerator is approaching 0, and the denominator is approaching 0. That right there is our indicator that we can do more. We try to direct substitute first, but what we get is this 0 over 0. This guy implies that we can do more. And what I mean by more is there's something that's causing a 0 both in the numerator and denominator, and maybe it's the same type of thing. Maybe it's the same kind of expression that I can cancel out. So this is when we kind of go then to our factoring. We try to break things down. Since I've got a quadratic in the numerator, I'm going to try to factor that as much as I can. The limit as x goes to -3 is then the limit as x goes to -3 of x plus 3 times x minus 2. And you'll get very good at, trying to match. If there's an x plus 3 on the bottom, then I'm looking for an x plus 3 somewhere on the top. At least that's what we're hoping for. It might not work that way. Right, but that's kind of one of the things we're hoping factors out of either the numerator or the denominator. Of course, I can cancel those two guys, and I'm left with the limit as x approaches -3 of x minus 2. This x minus 2 is like that g of x that the Theorem 2.7 talks about. Okay, this limit should have the same value as the original limit, and I can direct substitute here. I can actually plug in -3. -3 minus 2 is a -5. I'm done. It's good practice to kind of rewrite things, kind of come full circle. You can follow the equal signs backwards, but in general, we say that the limit as x approaches -3, the original limit I was tasked with, is exactly the result of that new limit, -5 there. Okay? So, I've got some strategy. I've got some things that I can do to approach and see if I can direct substitute. If I can't, then is there another way that I can do something to help myself? And trying to look for this kind of 0 over 0. So I'm going to try to give you a bulleted list here, or a enumerated list. The first thing we try to do is evaluate using direct substitution, of course, if possible. If you can plug in C to both the numerator and denominator and get a number, good. If not, we're stuck with number 2. Use Theorem 2.7. Okay, and the gist of that theorem, again, is that we try to find some other function g of x by some methods, right, factoring and canceling, there's more, so that it agrees with f of x for all x not equal c. And then we can use direct substitution. So situations where this occurs, factoring and canceling, of course. We're going to do some other examples, and they fall under these two categories. Rationalizing. This is something that we do with radicals. And finally, looking for a common denominator. Okay, and again, an indicator that we know that we should try one of these methods is if the numerator and denominator approaches 0 at the same time as x approaches c. Okay, if that doesn't happen, okay, so if I can't direct substitute because I've got a domain issue, and if the numerator and denominator do not both approach both approach 0, I misspoke, there's situations that arise where strategy for 1 and number 2 here just don't work. Or maybe I factor and cancel and I'm still getting a 0 in the denominator or something. This is where we fall back to number 3. We can use a graph or table or some other way to reinforce our conclusion. All right, so we have some other way to kind of fall back and say, this isn't seeming to work out by hand. I've got not many other ideas. Maybe I'm missing something. Let's look at a table or graph. And again, situations where that occurs when you're not getting 0 over 0, you might get something like a number over 0, or etc. Right? You might get some other form in your limit. 2 more examples I want to show you. The first, evaluate the limit as x approaches 0 of square root of x plus 1 minus 1, all divided by x. Okay, so again, kind of go through my strategy. Try to direct substitute. I see the numerator and denominator are both going to approach 0 simultaneously. So I'm going to rewrite, just get a little more room, and I got to think about what else I can do. The 0 over 0 implies that there's something else. Okay? And what I want to try to do is get rid of the x in the denominator, right? Because that's causing a 0 down below for sure. In the numerator, I've got, a couple of things up there that are causing a 0. I want to try to get rid of the x in the denominator, but the other part is the radical that makes things difficult to handle. Right? I can't really factor that very nicely, at least not into something that takes away a radical. So what we do in a situation like this is we multiply by 1, and that 1 is called the conjugate. Conjugate divided by the conjugate. We take what's in the numerator with our radical, we change the sign in the middle of that binomial, right, the 2 terms, we multiply by the conjugate. This guy here is the conjugate, and that is called rationalizing. So I look at that radical expression here, I change the sign to plus, and then I multiply both top and bottom by that expression. And I do that, I have to multiply by 1. I can't just multiply the top or the bottom, or I can't just cancel things willy-nilly. So I have to be careful. But the conjugate does something specific here. When I multiply that across the numerator, what I end up with is a difference of squares. So I'm going to distribute here in the numerator, take the square root of x plus 1 times the square root of x plus 1, and when I do that, I'm just going to get x plus 1, right? Those square roots are going to cancel. I distribute square root of x plus 1 to 1, and I've actually written things a little bit backwards here, so I did some multiplication in the, not the wrong order, it doesn't really matter, as long as I keep the signs, right? But I've got plus square root of x plus 1, and then I multiply minus 1 times the square root of x plus 1, and I get minus square root of x plus 1. And then finally, foiling the last 2 terms there, minus 1 times 1 is a negative 1. Okay? These guys will be able to simplify pretty quickly. My advice to you is to not multiply the denominator. Just leave the denominator as is. Again, that 0 in the denominator is coming from that x. We want to get rid of that. If all is going to work out, that x should disappear. Okay, so leave that in its factored form. Do not distribute that x. You can, it just makes things more difficult. Okay, so I see in the numerator, a bunch of stuff is going to go away, right? +1, -1 disappear, and those radicals are equal and opposite. You're always going to get a bunch of cancellations when you multiply by a conjugate like that, okay? All that's left in the numerator is x. Denominator, I'm going to leave how it is. And then I see where that cancellation is. I want you to note here, if you try to direct substitute at this step, you're going to get exactly what you had before, that 0 over 0. If you direct substitute before any cancellations are made, you don't get anything new, okay? So I've got to destroy those x's, leaving me with a 1 in the numerator, and I've written it in purple because that's like my new function, my g of x. It's going to behave exactly the same way as the original function, except exactly at 0. But in a little interval around 0, it behaves exactly the same way, and this g of x I can direct substitute 0 in, and I end up with 1/2. Square root of 1 is 1, plus 1 is 2, 1/2. Awesome. Pretty straightforward for the most part. Once you kind of get used to identifying when you have radicals versus when you can factor, and those situations kind of stick out. Okay, I want to do another example here. I want to evaluate this limit as x approaches 1, and I've got this compound looking expression, fractions inside fractions, 1 over x plus 1 minus 1/2 over x minus 1. All right, so again, try to direct substitute. First thing we do every time. If you want to try to work ahead, you feel free to pause and go through and see how far you can get. I try to plug in 1. I get 1/2 minus 1/2 over 0, 0 over 0. All right, so again, this indicates that I can try something else. I can do more. So I'm going to rewrite things here. And what I'm going to try to do is combine those fractions. So I've rewritten things. Those fractions, 1 over x plus 1 and 1/2, I'm going to try to make to have a common denominator. Right now, they really don't have anything in common, right? One's got a 2, the other's got an x plus 1. So what I do is I take both fractions and I multiply by 1, but the 1 is disguised as the opposite's denominator divided by itself. So on the left, I'm going to multiply by 2 over 2, and on the right, I'm going to multiply by x plus 1 over x plus 1. Right? I can only multiply by 1. I can't do anything else. Otherwise, it changes my problem, makes things not equal. Once I've done this, the common denominator should be there. 2 times x plus 1 is indeed the common denominator. Okay, so I'm going to simplify a bit. Limit as x goes to 1, denominator stays the same. Simplify both of those fractions, gives me 2 over 2 times x plus 1 minus x plus 1 all divided by 2 times x plus 1. It's tempting to cancel the 2's, cancel the x plus 1's. Be careful. That doesn't get me anywhere. I want to bring those fractions together. I actually want to subtract. Okay? And to do that, I've got a common denominator. I can subtract here. The numerators subtract 2 minus the quantity x plus 1. One of the largest mistakes you make there is with this minus sign. Just be careful. I'm subtracting the entire quantity x plus 1. So what that looks like, I distribute that negative. I take 2 minus x minus 1, and I'm left with 2 minus 1 is 1 plus a negative x, or minus x. So that's why we see the 1 minus x in the numerator. Divided by 2 times x plus 1, the denominator, the common denominator stays the same, all divided by that x minus 1 from the start. Okay? Again, at any point along the way, before there's any cancellations, if you try to direct substitute, you shouldn't get anything new, right? I would still get 0 over 0 here. So I'm looking for a cancellation, and I'm starting to see one. X minus 1 will hopefully disappear, and I'm looking at the numerator there, and I think it will cancel with this 1 minus x. I just got to flesh out the details. When I divide, it's the same as multiplying by the reciprocal. And what I do here, multiply by the reciprocal of x minus 1 is 1 over x minus 1. And that 1 minus x that was in the numerator, I'm going to factor out a negative. So I see x minus 1. Okay, now that cancellation appears. I divide out the x minus 1s. I'm left with minus 1 over 2 times x plus 1. Okay? And I can direct substitute. Again, in purple, because that's my g of x. I'm good to go. Plug in 1. I get minus 1 divided by 2 times 2 is minus a fourth. I could very easily verify this, with an online calculator, with a graph, a table, any of that. So the last two examples then are kind of the other two usual potential outcomes, right? With rationalization or looking for a common denominator. I encourage you to work through more examples of these. There's plenty online. There are loads of online resources for you. Practice more. I can't do all the examples that are possible, but just try to give you one of each so that you can then practice more and strengthen those skills and trying to figure out what to look for. Again, direct substitute, try to find a different function with those three kind of techniques. If all else fails, go back to a table or graph. Thanks for watching.